We choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. We cannot make the mystery go away by explaining how it works. We will just tell you how it works. So let's look at a few examples of this. And I'm going to focus on what happens in the single particle limit when we are putting single electrons or single photons or single atoms or single molecules through these slits. And we still see this interference pattern appear. So here's something from 2013. As you can see, controlled double slit electron diffraction. They've even used part of the diagram, this part, from Feynman's lectures in physics all the way back in '65. Pretty well updated it with these little annotations to show how they've made the slits and how they've made this mask, and this mask is movable so they can block one slit or the other slit. Let me just describe in words what they're doing here. So we've got slit number 1, slit number 2, and we have some source of particles here. And here we have a screen, or we have a detector, and in their case they've got a fluorescent detector, so when particles hit along there, it lights up and you see where the particle hits. Now, classically, you know what's going to happen. Let's say we shut off slit 2 and we just let the particles, we just have I don't know, firing tennis balls or whatever, or firing balls, firing objects at a hole, and then looking what happens. We're going to get some distribution, but it's going to be peaked behind that hole. Similarly, if we shut off number 1 and keep number 2 open, same type of thing. And maybe, depending on what sort of spread we have, they might overlap. But the important thing is, we've got some total probability, which is the sum of P1 plus P2. But we know quantum mechanically that's not what happens. What happens quantum mechanically is, instead of getting this distribution, the distribution we get when the slits are both open is something, and let's see if I can draw this correctly. Let's start with our peak. Now, looks like that, and then actually over here there would be other orders of diffraction, etc., etc. But we're just going to focus on that central peak, where you got maximum, minimum, maximum, minimum, etc., and it's symmetric, which is very, very different from the classical argument. And in the context of classical physics, this is pretty, and waves, this is pretty understandable, in that what's happening is that you get path differences between the waves from here and here. And those path differences give rise to constructive or destructive interference depending on the path difference, and therefore the phase difference between the waves. And that gives rise to this pattern. All well and good. The problem is, when you do it with single particles, one at a time, this is what happens. So you're seeing single electrons go through, one at a time. And they're going to shortly speed up the experiment a little bit, or at least speed up the video. But at the moment you can see it looks fairly random. But as the experiment progresses, and as you add more and more electrons go through, you're going to see that the double slit interference pattern starts to appear. So our probability is not just two heaps. Even though we're sending the electrons through one at a time, our probability is not just two heaps of particles, one behind one slit, one behind the other slit. Our probability is given by exactly the same mathematical function, which is, for those of you who want to know, and we'll come back to this, is basically something called a sinc function modulated or multiplied by a cosine function. But it's a mathematical function that is very well defined in terms of wave-like properties. And that's exactly what we get, except we've seen that interference pattern build up on the basis of just sending one electron through at a time. Not just electrons. This is a couple of years, no, actually 2016, from Miles Padgett's group at University of Glasgow. Same idea, but this time with photons. Again, it looks completely random, and as you build up, you're going to see the double slit interference pattern appear. Again, on the basis of single photons going through. One at a time. And it doesn't matter if those photons go through once every second or millisecond or microsecond or once every century. Ultimately, the pattern will build up even when there's only one particle passing through at a time. And this is why Feynman and many others have said the double slit experiment is the true, almost the only mystery of quantum. Because we still haven't got our heads around that. We're about to see how mathematically we can treat that, but in terms of conceptually what exactly is going on, we're still struggling with that. Can even do it with single molecules. The University of Vienna group, led by Marcus Arndt, have done heroic experiments, I would say, tour de force experiments over the last couple of decades on single molecules, sending them through. Most recently, you can see at the bottom here of the page, this was 2020, and it's actually just a couple of months ago. Matter wave interference of a native polypeptide, so a very large floppy organic molecule. My favourite example, however, is from a number of years back, again from the University of Vienna group. And as you can see, quantum interference experiments with large molecules. And there you go, there's the, as you can see on that page, there's the double slit experiment for C60, which is exactly the same as the double slit pattern we get for electrons, which is exactly the same as the double slit pattern we get for photons. But what I particularly like about this experiment with C60 is almost literally a molecular football, and it's about a nanometer across. And we've played around with C60, this C60 molecule, on various surfaces. Here are a couple examples on silicon surfaces. The bright blobs here, this and this, are the C60 molecules. The blobs in the background are single atoms, silicon atoms. Not only can we image this and it appears like a bright blob, but we can take the tip of our microscope, the scanning tunneling microscope, move it in close and push these things around. And not only do we push them, but they roll. It's about as close to a classical sort of billiard ball as we could get. And that's what's happening in these images. We've taken the molecule here and pushed it up the atomic rows until it's almost in line with this one. Indeed, we can pot the C60 in terms of, you think of it in terms of billiards, in terms of if there's a defect, if there's a missing atom in the surface, we put it in, and it's very, very difficult to get the molecule back out again. So this is, when you've pushed these things around, there's a real sense that it's a particle. And yet, in these experiments from the Vienna group, it's absolutely clear that under the other circumstances, it would behave exactly like a wave. And that wave-particle duality, if we want to call it that, some would quibble with that, but there's clearly, once we're down at that atomic, molecular, single particle level, it's clear that we've got to take the wave-like characteristics of these objects into consideration. Okay, let's go back to the double slit experiment and let's couple it to what we discussed a few minutes ago with regard to complex numbers, the complex nature of the wave function, how we get probabilities from getting the modulus squared of the wave function. Let's work that through for the double slit experiment so you can see some of these ideas come together. Okay, so we've got a double slit diffraction pattern, and that's given us the probability of finding the particles at different locations in space. How are we going to account for that quantum mechanically? Well, we know the classical probabilities don't cut it because it doesn't agree with the experiment. So let's, taking postulate 1 into consideration, let's consider this in terms of complex probability amplitudes. Remember, what we have is a complex number, and we're going to say for slit 1 we've got this, and for slit 2 we've got this, the certain phase factor, which we're going to call e to the I phi 1 here and e to the I phi 2 here. our total probability amplitude is psi1 plus psi2. Remember, that's still complex valued. How are we going to get our total probabilities out? Well, you know how to do this. What we're going to have in terms of a total probability, in contrast with the classical probability, is P total is equal to modulus squared of psi1 plus psi2. Or, equivalently, is equal to psi1 plus psi2 multiplied by psi1 plus psi2 complex conjugate. Okay? Let's keep working this through. Now that is equal to psi1 plus psi2. And the complex conjugate of this is the same as the complex of psi1 plus psi2 is the same as the complex conjugate of psi1 plus the complex conjugate of psi2. If you don't see that, make sure you work it through and just convince yourself of that with a couple of complex numbers. Now the complex conjugate of when you sum two is the same as the complex conjugates of the individuals summed. So let's just multiply this through. I'll start up here again. Let's multiply this through. So we're going to have psi1 by psi1 star plus psi1 times psi2 star plus psi2 by psi1 star plus psi2 by psi2 star. And every time I say star, you know I mean complex conjugate. Okay, so we can do something already here, which is very interesting. Psi1 by psi1 star is modulus of psi1 squared. Plus, let's take this one forward, and that's the modulus of psi2 squared. And then we've got these other terms. And these terms are absolutely crucial because this, we can see, is where our quantum comes in. This, remember, so we're talking about, classically we have P1 and P2. This is the probability for slit 1, and this is the probability for slit 2. So at this point, that's the same as the classical, but we can't stop there because we've got this. And that's where our quantum is. Let's work this through. Remember, this is the reason behind what I'm doing here is to show you the absolute key importance of phase. So what we have is psi1, psi2 complex conjugate, and psi1, psi2. That is the same as that. Okay, because we take the complex conjugate of the complex conjugate of psi2, we get back to where we started, and we take the complex conjugate of psi1, we get the complex conjugate of psi1. What that is twice the real part of psi1, psi2. If that doesn't make sense, let's do it over here. Can you see if I do it over here? Yeah, let's try it here. So, if we've got z plus z star, that's x plus iy plus x minus iy is equal to 2x, which is twice the real part of z. That's all I've done there. Taking a complex number, okay, it's a sort of compound complex number in that it's the product of these things, but the same rules apply. So it's twice the real part of that complex number. And in turn, what's twice the real part? Well, let's write this out. So twice the real part of what's psi1? Well, psi1 is the modulus of psi1 by e to the I phi 1 multiplied by the modulus of psi2, the modulus of psi2 by e to the, because it's the complex conjugate, e to the minus. Can we see that? It's just about on the board. Yeah, I'm just checking. That's a bit of a mouthful, to put it mildly, but it's going to reduce down to something even more straightforward. So P1 plus P2 plus twice the real part of psi1, psi2. And what's this? This is e to the I phi 1 minus phi 2. I think I'm going to have to move back up to the top of the board again. But just we've got the P1 plus P2, those classical probabilities, but then we've got this all-important quantum term. And that's directly related to the phase difference. And it's the phase differences. It's actually not the absolute phases themselves, it's the differences between phases, which is absolutely key in terms of quantum. Okay, so let me write this again at the top. Okay, I'll just move that up to the top of the board because we're running out of room at the bottom. And that, if we're looking for the real part of this, or twice the real part, is twice, well, psi1's, the modulus of psi1's real, modulus of psi2's real. What's the real part of that? Well, pause for a second, you could even pause the video. I think you know, I hope you know, the real part of that is cos phi 1 minus phi 2. Okay, the imaginary part would be sine phi 1 minus phi 2, or I times sine phi 1 minus phi 2. But we're only getting the real part. This is absolutely crucial. So, the phase is determinant. Let me stress that again. Not the phase, but the phase difference is absolutely essential in terms of how we define our probabilities here. Unfortunately, when we tell you about the time-independent Schrödinger equation, we we hide that phase term. And that's unfortunate. We have to start with the simpler systems. We have to start with the time-independent equation to build in the ideas. But losing that time dependence really loses so much of the essence of quantum mechanics. So our key equation is not this, which you've seen at length, and let's do it in one dimension. Our key equation is instead this. Again, let's keep it in one dimension. Which is the time-dependent Schrödinger equation. The little backwards d's rather than these d's, because this is now a function of x and t, two variables. Here we're only talking about, we're considering psi as a function of one variable, so it's a d. Now we're talking about two variables, so we've got to be careful and realize that we're doing partial derivatives here. So d psi dt, d squared psi dx squared, but in terms of partial derivatives in time and space. But notice how in this equation, we've lost the imaginary number, and now it's back in this equation. And finally, so I've mentioned complex numbers. We've got complex numbers embedded in everything we've done thus far, and certainly in this video, and we'll be seeing a lot of complex numbers. You could ask the question why, and that's a very good question for you to ask. And often, the answer will be, well, it just is. And I know that's not a very satisfactory answer. So there's actually a couple of papers just this year. First one in the American Journal of Physics, which is a great journal when it comes to education. And lots of lecturers read it to get insights in terms of different teaching styles, different learning styles, etc. And as you can see, it's got the title of Why Are Complex Numbers Needed in Quantum Mechanics? Some Answers for the Introductory Level. Now, right now, I would say none of those answers are going to be particularly satisfactory in that we haven't covered the background material. The first of those answers in that paper, however, we are going to cover next week. So it's related to Fourier analysis, and it's related to the relationship between position and momentum. The others we will develop either in the first semester or in the second semester. So I'm hoping by the time we get to the end of the quantum world, that paper will make a great deal of sense. On the other hand, there's this fascinating historical paper, as you can see, called Quantum Mechanics Keeping It Real, which I found online, which talks about Schrodinger's, basically, as the paper puts it, battle with reality, in terms of he was desperately unhappy with having to introduce complex numbers. And this quote really sums up where he was in 1926. What is unpleasant here, and indeed directly to be objected to, is the use of complex numbers. Psi is certainly a fundamentally real function, and therefore in equation 35 of my third paper, I should be good and write a cosine instead of the exponential. And then he changed his mind, so 1927, the wave function has to be considered as essentially complex. Are there other ways of doing quantum mechanics that don't need complex numbers? In principle, yes, but you have to bend yourself in knots mathematically to embed those. Complex numbers give us what we need in quantum mechanics in terms of the phase and the modulus, and those coupled together, so that when we take the modulus squared, we get a real number, but throughout our calculations, before we get that modulus squared, we've got the phase in there. Complex numbers sort of naturally lend themselves to that. So that's why we've got complex numbers. You'll find many arguments for and against complex numbers out there, some more informed than others. And finally, next time we're going to venture into reciprocal space, and we're going to look at something called Fourier analysis. Thank you for your attention. I hope this has been useful. I look forward to speaking with you in the next synchronous session. In the meantime, send me any comments, queries by email, or even put them down there under the video. Bye for now.